In this video, we'll introduce the Newton-Raphson method for root finding. This might be an algorithm that you've actually seen before, as it's covered in a lot of calculus classes. After studying this video, you should be able to explain how the Newton-Raphson root finding algorithm works. You should also be able to use Matlab to implement the Newton-Raphson method and compare the relative strengths of Newton-Raphson and bisection. Here's the basic idea. Newton-Raphson takes advantage of some available information about the behavior of the function to inform the next guess. Namely, we're going to use the slope of the function at the current guess to determine our next guess. So let's look at how this might work. So here is some initial guess, x1, and we want to find the root, which is where this function f of x crosses the x-axis. And what Newton-Raphson does conceptually is takes the slope at that function, so we draw a tangent line using that slope at that point, and we'll use that to determine our next guess, which we'll call x2. Then take a function evaluation at x2 and the slope at x2 and use that to get our next guess, call that x3, and so on until eventually we get to the root. And by using some information about the behavior of the function, we're able to get closer to the root faster. And that's one of the main motivations of the Newton-Raphson iteration, is we will generally get faster convergence on the root compared to bisection. So let's look at how we can develop this algorithm. So if we look again at the ith step, so now I've written this in terms of x sub I and x sub I plus 1, and coming up with that guess we will call the ith iteration. And the slope then, f prime of x, that we use there can be written as the rise, which would be here, f at x sub I minus 0, over the run, which is right here, or x sub I minus x sub I plus 1. So what we'll then do is just solve this equation for xi plus 1. And everything on the right hand side is known for the ith iteration, and then we can use that to get our guess for the next iteration. And just like bisection, we'll keep doing this over and over again until the scheme converges, and we know that it converges when the approximate relative error is less than or equal to the stopping criterion, the absolute value there of the approximate relative error. So let's look at a Matlab function to implement this. Here's a Matlab function, again building on that latest version of our bisection function that includes var argin and variable number of inputs with defaults for ES and the maximum number of iterations. And the implementation of this actually takes quite a few less commands than bisection. We'll see all we have to do is within that for loop for the iterations is just recalculate that single equation where we are getting our new guess from our old guess, and simply just implementing that iteration scheme, xi plus 1 is equal to x sub I minus f of x sub I over f prime at x sub I. And so another difference here is we need f prime, and we bring that in as the second input. So we have actually two functions coming in here. For this algorithm, not just one. And a key thing you need to be careful of is you need to be careful with parameters here, because you might have parameters with the first function itself, fun, that formulates the roots problem, and you might also have parameters associated with df/dx, and you just need to be careful to keep all of that consistent. So let's look at how this performs relative to the bisection method. So we looked at this in a previous video. That's the blue line for the bisection method, and that's the convergence behavior as we decrease the stopping criterion for the roots problem e to the x minus 2 minus x equals 0. Now the red results with the stars are for Newton-Raphson, and we see that Newton-Raphson only takes 5 or 6 iterations for each of these cases, whereas bisection ranged from about 11 iterations at the loosest tolerance all the way up to 28 iterations at the tightest tolerance. So it looks like Newton-Raphson, at least for this roots problem, is indeed quite a bit more efficient. So let's talk about some other pros and cons of Newton-Raphson. As we saw, it does converge significantly faster than bisection. And in fact, we're not going to show it here, but you can show that the error of the i+1th iteration is roughly proportional to the square of the error of the ith iteration. And this is called quadratic convergence, since it's proportional to the square. I didn't show it either, but for bisection, the error of the next iteration is roughly half of the previous iteration for bisection. And that shouldn't be surprising because we're cutting the interval in half with each of those bisection iterations. So we do see that Newton-Raphson converges quite a bit faster. One con of Newton-Raphson is that some functions show slow or poor convergence, and I've got some examples of that over here on the side. Here's an example where it diverges with this function going from an x0 here, and x1 actually gets farther away from the root, and then x2 gets even farther, and eventually we're diverging. Here's one where we diverge again. Another diverging problem. And another diverging problem. So there's numerous cases. Here there's no root shown anyways. And again, there's no root nearby. And that's one of the things that we see is if those initial guesses are closer to the root, then it's more likely to converge. So it puts a little bit more requirement on our initial guess. Recall for bisection, as long as that root lies in between the initial bracket, the bisection method is going to converge on it. For Newton-Raphson, it usually converges as long as our initial guess is somewhat close to the root we're seeking. Another con sometimes is that this requires the calculation of an analytical expression of the first derivative. Now that was easy in this case with the exponential function, but sometimes you have functions, particularly with the complex mathematical models that arise from empirical results, where that analytical expression of the derivative could be quite cumbersome. So next we'll look at another method that addresses this second con called the secant method.